Yeah. Hello. Good morning. This is Aerodynamics lecture series on chapter 3, which is fundamentals of Inviscid incompressible flow. And the main content of this chapter is about basic aspect of Inviscid incompressible flow. Basic equations of flow like Bernoulli's equation, Laplace equations, Euler equations, and Navier-Stokes equations. Then the content also covers some elementary flow types such as uniform flow, source flow, doublet flow, vortex flow, and combination of uniform flow with source and sink. And such kind of superposition is also included in this. It also covers the non-lifting flow over cylinder, lifting flow over cylinder, and the source panel method, the numerical method which we use, source panel method is there. And also it also consists the theory and generation of lift using the Kota-Joukowski approach. The purpose of this chapter is to establish some fundamental relations which are applicable to Inviscid incompressible rotational flow, and to discuss important flow fields and its application. So mainly we emphasize on the development of Bernoulli's equation, the development of the governing equations for Inviscid incompressible rotational flows like Laplace equation, for the velocity potential as well as for the stream function, and to present some elementary flow patterns, as I have said, and how they can be superimposed to synthesize both the non-lifting and lifting flow over cylindrical shape, circular cylinder, and any arbitrary shapes like and also aerofoils also. Actually, it is better to define some important words. Actually, these are most known words in your fluid dynamics course. However, just to remind them, what is Inviscid flow and what is incompressible flow? So Inviscid flow is a type of flow, fluid flow, in which the viscosity of the fluid is not considered and it is neglected. So no viscous forces are considered, and the flow is dominated by pressure and inertial forces, governed primarily by the Euler equation. So here the Euler equation is the one. Again, when we come to incompressible flow, it is a flow, a fluid flow, type of fluid flow in which the fluid density is considered constant. That means the rate of change of density is zero, because the density is considered constant, and the flow is within low speed flow. Okay, so maybe the velocity range is up to Mach 0.3. Okay, so in the mathematical representation, the incompressible flow is denoted with the gradient of velocity is equals to 0. Okay, so the gradient of velocity. So Inviscid incompressible flow combines both assumptions. One is the no viscosity assumption, and another is the constant density assumption. So the governing equation are the continuity equation governs here. So incompressible flow is governed by the continuity equation, so which ensures the mass conservation, and the gradient of velocity is 0. And directly starting from the Euler equations for Inviscid flow, we have density. The rate of change of velocity is there, and the gradient of velocity, which is equals to the pressure minus of pressure, gradient of pressure plus the body force. Okay, that body force is due to the presence of gravitational force. So what are key assumptions throughout the discussion of this lecture? One is fluid is ideal, non-viscous in case ideal fluid, and flow is steady. That means the rate of change of flow field variables are zero, and density is constant, so there is no density variation. So that means incompressible. And the effect of boundary layers and the viscous shears are ignored. Okay, so the boundary line effect, the viscous boundaries are not considered throughout the discussion. So these are the key assumptions to be understood with the scope of this course. Now let's start to develop the Bernoulli equations. So the theoretical fluid dynamics faced by the work of John and Daniel Bernoulli, and they propose the relation between pressure, velocity, and elevation, which is represented with the first equation, which is P plus half rho V square plus rho GZ, which is constant. That is the Bernoulli equation, well-known Bernoulli equation. And we demonstrate this Bernoulli equation using the Venturi tube apparatus. So on that, we can find different cross-sectional geometry or area difference. Maybe in some case, if the Venturi apparatus is inclined, there may be elevation difference may appear. But in most cases, we consider that the altitude, the elevation is in constant elevation. And we consider the height as the same. Therefore, actually here we have pressure force. This is the what you call dynamic pressure, static pressure, dynamic pressure, and this is the potential energy. Okay, so potential energy, pressure energy, and kinetic energy. Okay, so these are considered constant. That is the Bernoulli equation. Okay, so how we can drive Bernoulli equation? To drive Bernoulli equation, we consider some flow along streamline in three-dimensional space, and the equation of streamline is from the previous chapter is given. So the streamline equation is dx over u, velocity in the x direction, dy over velocity in the y direction, dz over the velocity in z direction are equated in this manner. So this equation provides us three different equations. Okay, that equations are called streamline equations. So, for example, if we consider the x and y, we can take this part of these two equations and we equate. What we can get is v times dx is equals to u times dy. That is one equation. Again, we can consider this equation, the y component of equation is the z, then we can get one equation again. And the third equation is just the x component with z component that gives us the third equation. So from this only we can get three equations. Let's use the common values that ds over v. V is actually the velocity, the magnitude of velocity. So the velocity vector is defined in this manner. V is equals to u in the x, u in the I, plus v in the j direction, plus w in the k direction. So that is the velocity vector. So ds is the surface. Okay, when we are defining the boundary conditions, we'll discuss that ds of the boundary. So that is the surface on which we are giving emphasis. So for the overall velocity, the magnitude of velocity should be calculated from this equation. And now for steady Inviscid flow, the Euler equation. This is just an Euler equation. From the previous, we have here an Euler equation is there. Yeah, this is Euler equation. So considering this Euler equation, what happened? Projecting the Euler equations along the streamlines, what we can get is rho v dv over ds, which is equal to minus of dp over ds minus rho g dz ds. So dividing both sides by ds, we have left what? Rho v dv, which is equal to minus of dp minus rho g dz we left. Okay, so yeah, this is the equation. And then we integrate this equation along the streamline. So it provides us integral of rho v dv plus integral of dp plus integral of rho g dz in the along streamline. So that gives us half rho v square plus p plus rho gz, which is equals to constant. So this constant is the integral constant. So this is well-known Bernoulli's equation, and we can represent it in terms of just dividing them by density. We have p over density plus v square over 2 plus gz, which is equals to constant along the streamline. So that the first term represents pressure energy per unit mass. The second term indicates kinetic energy per unit mass. And the third term is potential energy per unit mass. So in most cases, the third term will vanish. Why? Because we assume, especially if there is no in our Venturi tube apparatus like this, for example, if I draw this type of apparatus, so and assume that this is the center line. Yeah, this is the center line for the apparatus, and we may have a reference point, some reference point. So our Z is equally everywhere. If I take, for example, this cross section, this section, okay, so it is just jammy. So this Z is equal with this Z again. Again from here to here, Z is the same. So that this term may vanish from for our simplified analysis. Therefore, what is left there? The remaining thing is P over rho plus V square over 2. That means pressure and kinetic energy. Actually, this is actually dynamic pressure. Half rho V square is called dynamic pressure. And this is static pressure, and this is pressure due to potential. Okay, so that is the meaning. So what is the physical significance of Bernoulli's equation? That is our question. That is, when the velocity increase, the pressure decrease. And when the velocity decrease, the pressure increase. So the area where high pressure is there is low velocity. Okay, so the formula itself shows that when pressure increase, velocity should be decreased in order to get same constant magnitude, because our p plus half rho v square plus rho gz is equals to constant. Okay, so the Bernoulli's equation was derived from the momentum equation. Hence, it is a statement of Newton's second law. The Bernoulli's equation itself is the statement of Newton's second law. That is the conservation of momentum. What it says, Newton's second law? the Newton's second law is just d of mv over dt, which is equals to the net force F net. Okay, that is Newton's second law. Okay, therefore, it is for an incompressible Inviscid flow type with no body force. We consider that the Bernoulli's equation can be also interpreted as either Newton's second law or energy equation. So it can be interpreted in different manners. Okay, from this momentum conservation, we will find the Bernoulli's equation also, and as the same, we can find it from the energy conservation. Okay. Now, based on what we have discussed it, let us take one example. Consider an aerofoil in the flow at standard sea level conditions, where the free stream velocity is 50 meters per second. And at a given point on the aerofoil, the pressure is 0.9 times 10 raised to 5 Newton per meter square. Then what is the velocity at this point? Okay, so we have given two parameters. One is the free stream velocity at sea level is known, density is known for the air. Okay, the air free stream velocity is actually most of the time it is 1.225. So let's consider it 1.23 kilogram per meter cube. And the free stream density in the sea level condition is known, which is 101 times 10 raised to 5 Newton per meter square. Therefore, directly applying the Bernoulli's equation for the constant elevation, just if the elevation is constant, the potential term will be vanish. What left? Only the static pressure and the dynamic pressure part left. So pressure at free stream plus half rho v the square of the stream condition, which is equal to P plus half rho v square, is the general formula from the Bernoulli's equation. So that gives us the final V, which is 2 times of free stream pressure minus pressure at that point divided by the density of the point. So actually it is given the density of free stream already given, so that we can compute it. Okay, so that gives us about 142.8 meter per second on the point. Okay, so let's see another second formula. Actually, they are almost the same. Okay, but consider the Inviscid incompressible flow of air along the streamline. The air density along the streamline is given, which is 0.002377 slag per feet cube, which is actually free stream density, air density at standard sea level condition. At point 1 on the streamline, the pressure and velocity are given as 2116 pound per feet square and 10 feet per second, respectively. Further downstream at point 2 on the free streamline, the velocity is 190 feet per second. Calculate the pressure. At point 2. What can you say about the relative change in pressure from point 1 to point 2 compared to the corresponding change in the velocity? So these are two questions. So for that, we directly use considering the same elevation still, elevation is considered the same, so that the elevation, the potential part will be taken out. So P1 plus half rho V1 square, which is equal to P2 plus half rho V2 square. So rearranging this, what we can get finally is P2 is equal to P1 plus half rho times V1 square minus V2 square. So on the same elevation, the density also is the same. So we have same density. That's why. So directly substituting the values, what we can get is the pressure 2 is 2073.2 pound per feet square. So we have given pressure 2116. And now what we obtain here is 273. So there is difference. The difference is about 42.8. Okay, so this is the way. Okay, now once we understand the concept of Bernoulli's equation, let's come to the condition of velocity for incoming flow. So let's first consider the definition of incompressible flow, that density is constant, and irrotational flow, that the divergence of velocity is zero. That is a definition of incompressible flow. Okay, incompressible flow is defined in terms of the velocity divergence of velocity, which is zero. Okay. Since density is mass per unit volume, then the fluid element of fixed mass moving through an incompressible flow field must also have fixed and constant volume. So there is no volume change. Okay, recall that the divergence of velocity is physically the time rate of change of the volume of moving fluid element per unit volume. Therefore, for an incompressible flow, the volume of the fluid is constant. That means the derivative of the volume with respect to time, which is zero. Okay, that indicates for the compressor, the divergence flow is divergence of velocity is zero. Okay, so this is actually a substantial derivative form. The capital derivative indicates that the derivative is substantial derivative. Okay. So now we have seen the principle of mass conservation and energy conservation. From that, we already developed the Bernoulli's equation for an incompressible Inviscid flow. Okay. So for an irrotational flow, we have a velocity potential pi defined as pi is equals to the divergence of v is equal to divergence of velocity. Okay. Therefore, for the flow that is both incompressible and irrotational, this equation is simplified to the Laplace equation. So this is Laplace equation, which is directly obtained from equation 339, which is given here. The velocity divergence of velocity is equal to zero. And then we have this equation for the irrotational flow. So combining these two, what we can get is the velocity potential is a function of Laplace equation. So this Laplace equation is a linear equation, which is having a solution of n number of linear solutions will be there. Okay, so for our convenience, most of the time we define this Laplace equation in terms of Cartesian coordinate, cylindrical coordinate, or spherical coordinate. But in most cases, we practically use for Cartesian coordinates and cylindrical coordinates. But for the complex case, we may also use a spherical coordinate that is also applicable. So for that, in the Cartesian, the pi is defined as pi of x, y, z in 3 dimension. So the Laplace form of the pi, which is the partial, actually, these are all partial derivatives. Okay, partial derivative of pi are there, so which gives us 0. In the case of cylindrical coordinate, we define it in terms of pi of r, theta, and z. So r is the diameter of cylinder, theta is the angle, and z is the length of cylinder. Okay, so because of that, we define it in terms of r, theta, z. That is called cylindrical coordinate. So again, in the spherical coordinate, we define it in terms of r, theta, and the pi. So cylindrical coordinate is defined in terms of radius of the sphere, angle theta, and angle pi. So this is what we call spherical coordinate. So now our Laplace equation for two-dimensional incompressible flow, we can define the stream function. Previously, what we have defined, the pi is the velocity function. Now, psi is the stream function. So psi is defined as d psi dy, which is equals to the x component of velocity, which is u. And minus of d psi dx gives us the y component of velocity, which is v. Okay, so this is definition for stream function. So the continuity equation of the divergence of velocity is equal to 0, expressed in Cartesian as the divergence of velocity, which is equal to d psi over dx plus dv over dy, which is equal to 0. So that is the continuity form. And it gives 0. Substituting this double start equation with equation 344 provides what? Yeah, when we substitute this equation into here, you can clearly see this gives us 0. Okay, this is because mathematically the second differential of dx dy and dy dx are same, so that it immediately satisfies the continuity equation. The incompressible flow, it is irrotational also, and the irrotational condition is stated as dv dx minus du dy, which is equal to 0. So we can substitute those values of the v and the u values. Okay, v is minus of d psi dx, and the u is plus d psi dy, so that substituting these values, the final result is d square psi over dx square plus d square psi dy square, which is equal to 0. And this also is another form of Laplace equation in terms of stream function. So both stream function and the velocity function satisfies the Laplace equation. Okay. Therefore, we can conclude these two equations, the equation 340 and the equation 346 of the velocity function as well as the stream function, and the velocity potential as well as the stream function. We conclude or we can judge something. So any rotational incompressible flow has a velocity potential and stream function that both satisfy Laplace equation. The second conclusion is any solution of Laplace equation represents the velocity potential or stream function for an irrotational and incompressible flow. So these are the two conclusions. So how we can find solution for this stream function as well as velocity potential? Okay, so the Laplace equation is just a second order linear partial differential equation. And it is a linear equation because the sum of any particular solutions of linear equation is also a solution for the equation, because we are just superimposing the particular solutions of different linear equations. For instance, if pi1, pi2, pi3, and pi n represents n separate solution of equation of 340 of the velocity potential, then the sum of this pi is equal to pi1 plus pi2 plus pi n is also the solution for this equation, for the velocity potential. Okay, so that is the meaning. So in the case of irrotational incompressible flow, which is governed by the Laplace equation, and Laplace equation is just as linear, so that we conclude that the complicated flow pattern for irrotational incompressible flow can be added together or superimposed together for a number of elementary flow types. So we'll discuss what are those elementary flows. We'll discuss them later, one by one, and how we can combine or superimpose them. So a number of elementary flows that are also rotational and incompressible. Therefore, we develop flow field solution for different elementary flows, then add or superimpose them, these elementary flows in different ways to obtain solution. Okay, so if we consider rotational incompressible flow field over different aerodynamic shapes, for example, spherical shape, conic shape, aerofoil shape, and other shapes, each flow is going to be different. They are different because their boundary conditions are different. And the streamlines and the pressure distribution over each of these shapes are quite different. Therefore, these different flows are all governed by same equation, which is Laplace equation of the either velocity potential or the stream function. Okay, so how do we obtain different flows for different bodies? The main answer for this is using different boundary conditions. In each case, the boundaries are different, so that we use boundary conditions. And what are the two main boundary conditions which are useful for our analysis? That is the question. So let's see those two boundary conditions. For example, let's consider the external flow aerodynamics over some stationary aerofoil or any kind of stationary body. On that, you can observe the far stream boundary conditions, the far stream condition, or the infinite boundary conditions are there. And there are also boundaries just at the point where the interaction takes place, which are surface boundaries are there. And there are also far boundary conditions, infinity boundary conditions, okay? So this figure illustrates the boundary condition at infinite end on a body. So, for example, the pressure and the velocity at this point, tangential velocity is there. The normal component of velocity is not considered. It is considered zero. And if we take this region that is far away from the front or far away from behind of this aerofoil, or somewhere above and somewhere below, far away. So these are two boundary conditions which we consider. Okay, at infinite boundary is these boundaries, okay, which are shown with infinity. And the surface boundaries are like this. For example, psi is equals to constant over the surface. YB is equals to f of x. Okay, y is representing the location of each point. S is the surface of the aerofoil, and N indicates the point normal to the surface, that where the pressure is acting on it. Okay. So if we consider irrotational incompressible flow field over different aerodynamic shapes, sorry, this is the same thing. So the flow is bounded by, one is the free stream velocity, a flow that occurs theoretically an infinite distance away from the body, and the second is surface of the body itself is considered another boundary conditions. So applying these boundary conditions, we can find solution to each of the different geometric shapes. So what are the infinite boundary conditions? So the far away from the body, in all directions, the flow approaches the two uniform stream conditions. So let V infinity be aligned with the x direction, as shown in the previous figure. At infinity, U, which is equals to actually from the velocity function, from the velocity function we have, d pi, the partial differentiation of pi with respect to x gives us U, and the partial derivative of psi with respect to y gives us U. So this is the free stream velocity V. Okay, so this free stream velocity V is this either d psi over dy, or it is d pi over dx. Another, the v, the vertical, the y component of velocity, which is d pi dy, which is equal to d psi dx, which is equal to 0. So these are the infinite boundary conditions. So from these two equations, the boundary conditions on velocity at infinity, they apply at infinite distance from the body in all directions, above and below, and to the left and to the right. Okay, because we can observe above and below, in front and behind. So this is one of the boundary. The second is the wall boundary conditions, or on the surface of the object. So for Inviscid flows, the velocity at the surface can be finite, but because the flow cannot penetrate the surface, the velocity vector must be tangent to the surface. Therefore, this wall tangency condition is just illustrated here, there in the figure. So if the flow is tangent to the surface, then the component of velocity normal to the surface must be 0. So Vn is equals to 0. So we can represent that Vn, V dot n indicates the normal component of velocity, which is 0. d psi over dn is equals to 0 on the wall. Again, from the equation 348, the boundary condition for velocity at the wall, it is expressed in terms of pi. If we are dealing with psi rather than pi, then the wall boundary condition is also similar. That is d psi over ds is equal to 0. Okay, so this is d psi velocity at that surface. d pi dn is equal to 0. d psi ds is equals to 0. So these are the two wall boundary conditions. Therefore, psi is constant is the equation for the streamline. Therefore, if the shape of the body is given by y of b is defining y of b is equal to f of x, is the shape of the which defines the shape of the body, then psi of the surface is equals to psi at y is equals to yb, which is constant. So in terms of velocity component u and v, the wall boundary condition is obtained from the equation dyb over dx, which is equal to u over v over u at surface. Okay, so this thing defines the geometric condition, and the second term indicates the velocity with the surface. So just from this, we also can find the stream function also. So this is about the introduction part of this chapter. Now we are going to see different elementary flows. Okay, different elementary flows be analyzed in the upcoming sections. So among them, uniform flow, that the first elementary flow is the one. Okay, so what is that uniform flow? As you see from the figure here, all the streamlines are moving in the forward direction. Okay, the arrow indicates forward. And on that, if you take some curve C, if you take some curve C with height h and length L, and the flow is characterized V is equals to V infinity. And on the uniform flow here, psi is equals to constant. In the horizontal, psi is constant. In the vertical, pi is constant. Okay, so a uniform flow is just a physically possible incompressible flow that it satisfies the velocity divergence is equals to 0, and that it is irrotational. It satisfies okay, delta pi is equals to V. Okay, so from that context, we'll define it. Okay, so just examining the above figure, what happened? D pi dx is equals to u from the boundary condition. D pi dy is equals to V, and that u is equals to V infinity, and V is equals to 0. The x component of velocity is equals to V infinity, and the y component of velocity is equals to 0. Okay. Why? D pi is constant in the vertical. Okay. D pi is constant at vertical. So the differentiation of constant with respect to y gives us 0. D pi, okay, in the x direction, actually, in the x direction, it gives us V infinity. So these are our boundaries. So integrating this equation, the first equation, what we can get is pi is equals to V infinity x plus f of y. So f of y is an integration constant here. Okay, f of y is a function of y only. And integrating the second equation with respect to y, what we can get, pi is equals to constant plus g of x. Therefore, this f of x is something constant here. F of x is now constant. Therefore, combining the two equations, what we can get, pi is equal to v infinity x plus constant, right? Yeah. In a practical aerodynamic problem, that pi is always used to obtain the velocity by differentiating that is the gradient of pi is equals to v. Since the derivative of the constant is 0, we can drop the constant from our equation. So finally, pi is equal to v infinity x is taken. In similar way, okay, so this equation indicates what? It is velocity potential for uniform flow with velocity v oriented in the positive x direction. So this is for uniform flow. Let's also consider the psi function, the stream function psi. D psi dy is equals to u, which is equals to V infinity, and d psi dx is equal to minus of V, which is 0. In similar fashion, we are also getting psi is equals to V infinity y. Psi is equals to V infinity y, pi is equal to V infinity x. The 353 and 355 are very important equation in terms of velocity, potential, and stream functions. Therefore, for uniform flow, we consider these two equations. Okay. Someone can define this in terms of the cylindrical coordinate system. Okay. Actually, we can decompose the components, the x and the y. So here this r can be decomposed into x and into y. So for x, it is cos relation, and for y, it is sine relation. Okay. So theta is there, angle theta. Therefore, we can represent, okay, the x component, x is equals to r cos theta, and y is r sine theta. Okay. So, actually, I can put it here with pointer. Okay. X is equals to r cos theta, y is equals to r sine theta is there. Yeah, sine theta. So the two equations are the velocity potential x. So for x, we consider r cos theta. And for y, we consider r sine theta. Therefore, these are pi is equal to v infinity r cos theta and psi v infinity r sine theta. So consider the circulation in uniform flow. So when we are, the definition of circulation from our previous chapter is given like circulation is equal to the circle integral of VDS, okay, for a given curve C. C is defining the curve. You see, this is some curve. Okay, so this defines for the whole path of the integration is for the whole path, and the velocity V is there and ds. Okay, so this is the circulation in uniform flow. Okay, so let's consider the curve C in above figure, as you have seen, be the rectangular shown at the and which is defined thickness h and length L are the given curve. So for that, what we can do is the integral v dot ds gives us v is along the length minus of v times length L, and along the thickness there is no velocity, so it is 0, plus actually from the bottom and the top, when we are coming to this direction, what happens? V infinity L plus on the thickness direction, it is 0. Okay, so which is equal and opposite magnet, so the circulation is equal to 0. So circulation around any closed surface in uniform flow is 0. So this defines the circulation around any uniform geometry surface is 0. Okay, so our shape is like this. Okay, rectangular shape having h here, h here, L here, L here. So starting from somewhere, our flow can be either from this direction to this, or it can be from this direction to here. So the sum of circulation is equal to 0. Okay. So for any closed curve in uniform flow, especially in the time of uniform flow, the circulation is 0. Okay, so V dot ds, which is equals to 0. The above result is consistent with our previous equation, which is provided in the previous chapter, which is this chapter. So this is what we call the divergence of velocity. Not divergence, but gradient of velocity. Okay, velocity gradient dot ds is which is 0 also. Now let's consider another pattern of flow. The source flow is the second elementary flow type considered here. So this source flow, you see, you have a point source and all the flows are outward from this point. In the same way, we have sink flow also. The flow is towards to the same point, O. Okay, source flow and sink flow. Okay, so we have VR at some theta angle, and along the stream, psi is equals to constant, and at some r, pi is equals to constant. Okay, so about this dotted line, pi is constant, and about these lines, psi is constant. So this is the source and sink representation. Okay, so how we can develop the equations. So examining this figure, we see that the velocity components in the radial and the tangential directions are VR and V theta. Obviously, we represent the radial component of velocity by VR and the tangential velocity V theta, where V theta is equals to 0. Okay. It shows one, the source flow is incompressible flow. That is, the divergence of velocity is equal to 0 at every point except the origin, where the divergence becomes infinite at that origin. Source flow is irrotational also. Okay, that that indicates in the source flow, the stream are directed away from the origin, and the origin is a singular point. The origin is a singular point, okay? So we can interpret this singular point as a discrete source or a discrete sink of a given strength, okay? The second is sink flow. So the opposite to the source flow is the sink flow. So all the flows are towards to a single point, okay? Where the streams are directed towards to the origin. For sink flow, the streams are still radial lines from a common origin, okay? Along which the flow velocity varies inversely with distance from point O. Okay? Sink flow is also simply a negative source flow. Okay? So let us examine the velocity field induced by source or sink. By definition, the velocity is inversely proportional to the radial distance. So you can define velocity V, okay? Velocity V is proportional to the radial distance r. Okay, so the velocity variation is possible flow because it yields the divergence of velocity is equals to 0, and the velocity variation for which the divergence 0 satisfies the radial flow for the radial flow. Okay, so VR is equal to C over R. So C is some constant, and the V theta is equal to 0. The tangential velocity is 0. Okay, so the value of constant is related to the volume flow from the source. Okay. So let's consider the mass flow across the surface of the cylinder of radius r and length L. So we have radius r is there, and the length of this cylinder is L. So the elemental mass flow across the surface element ds. So we have surface element ds is here at some theta angle. Okay. So which is rho v ds. Okay, rho v ds, which is equal to rho times vr. Now the velocity here v is the radial velocity. Okay, and the ds is the surface, so it is r d theta times 1. R d theta times 1. So for the unit distance, so you have this is r d theta is there. And the ds is defined in terms of length L. Yeah, length L is r d theta. R d theta is the arc length here. Okay, let me define those points. So this length is r d theta, and L is this length, so that this surface ds is r d theta times L. So that is the volume. Okay. The elemental mass flow, actually, mass flow across the surface. This is mass flow. So the total mass flow across the surface of the whole cylinder, this is for only differential element, which we defined. Okay. For the given small differential element, we have rho v ds, which is equal to rho v vr times r d theta times L is for differential element. But for overall, we integrate the cylinder from 0 to 2 pi. Okay, rho times Vr times R d theta times length from 0 to 2 pi, which gives us 2 pi R L times rho times Vr. Okay, 2 pi R. R is the radius of the cylinder, L is the length of the cylinder, rho is the density, Vr is the radial component of velocity. So the mass flow rate is defined in this way. So the density, it is just mass over volume. Okay. So we can define the mass flux, actually. This is mass flux. The rate of volume followed by the mass flux. So V dot is equal to m dot over density. So which gives 2 pi r LVR. Okay. So the rate of mass flow per unit length along the cylinder is V dot over L, and it's denoted by some source strengths. This is a definition for source strengths. Okay, source strength is equal to V dot over L, which is 2 pi r VR. Therefore, the radial velocity is defined in terms of the source strength divided by 2 pi r. So this 2 pi r is the circumference of the cylinder, actually. Source strength divided by circumference of cylinder. So that as r varies, when r is having large value, our radial velocity is small. As r is very small, the value of VR is high, so that it is inversely proportional. Okay, so radial velocity is inversely proportional with radius. That is the definition. And our C is now, because we defined, initially we defined VR is equals to some constant C over R. So just observing this equation, our C is now what? It is the source strength divided by 2 pi. That is constant C. So it is the rate of volume flow from the source per unit depth perpendicular to the page. And the typical unit of source strength is meter square over second, or in the imperial unit system, it is feet square per second. Okay, so this equation, positive value of source strength represents a source, whereas negative value represents a sink. So this inverted V indicates the source strength, and it is positive value is source, negative is sink. Okay, so they are so the velocity potential for source can be obtained as, so d pi dr gives us Vr. Okay, d pi dr gives us Vr, which is source strength divided by 2 pi r. And in the radial direction, 1 over r d pi d theta, which is v theta, which is equal to 0. So integrating the first, what we can get is pi is equals to, this is just velocity potential, pi is equal to the source strength divided by 2 pi r, ln of r plus f of theta. So integrating equation with respect to theta also, we can get pi is equal to constant plus f of r. So it is a function of constant terms of r. So in similar fashion as we have done before, pi is equal to, just neglecting the constant f of theta and f of r, what we have left is pi is equals to the source strength divided by 2 pi ln r. So this is source flow when we consider source flow. If it is considered sink flow, we can take minus. Okay, so this equation represents the velocity potential for 2D source flow. Again, considering the stream function, we can obtain 1 over r d pi d theta, which is equal to Vr, which is equal to source strength over 2 pi r. And that gives us, and the second equation is minus of d pi dr is equal to v theta, which is 0. So that the tangential velocity is 0. Therefore, in similar approach also, what we have, psi is equals to source strength divided by 2 pi theta. Theta is the angle. So that equation indicates the stream function for 2D flow, and the equation of the stream can be obtained by performing some integration and so the equation of stream function can be obtained by setting equation 372 equal to a constant. So that psi is equals to the source strength divided by 2 pi times theta, which is equals to constant. And this equation, that equation 373, we see that theta is constant, which in polar coordinate is the equation of straight line from the origin. Okay, so this is just a equation of a straight line. Considering these are some constant value, so theta is constant, so psi is a equation of, and this equation is consistent with the picture of the source flow sketch. Okay, and equation 367 gives an equipotential line as R constant. Okay, if R is constant here, okay, what happened? We have equipotential line. Okay, equipotential line. But if R is vary, it will vary with the value of phi is vary. The streamline and equipotential lines are mutually perpendicular to each other. So which one is equipotential line? Let me show you in this figure. This is an equipotential line, okay? Equipotential line, and these are streamlines. So the point where psi is constant is equipotential. So to evaluate the circulation for the source flow at every point, so this equation satisfies. So this equation is directly taken from the previous chapter. Okay, so let's combine the uniform flow with source flow. Now this is the superposition principle. We are superimposing two different flow types. As we have discussed, each of the flow pattern satisfies the Laplace equations, so that the solution for them will superimpose and produce also another equation which also satisfies the Laplace, right? So that they are the linear algebraic equations. So when we are combining uniform with source flow, we have uniform flow of, for example, psi is equals to V r sine theta. And in the case of source flow, we have psi is equals to the source strength divided by 2 pi theta. So when we superimpose them, we can get this answer. So our psi now, the new psi for the combined effect or superimposed equation is V infinity r sine theta plus the source strength divided by 2 pi theta. Okay, so that is what? So this is the equation that we developed from the two. Since 357 and 372 satisfies our solutions of Laplace equations, the 374 also satisfies Laplace equations. 374 means the superimposed equation. Okay, this equation satisfies. So that means what? The stream of the combined flow R obtained as psi is equals to constant. So that means V infinity R sine theta plus the source strength over 2 pi theta is constant. That is the satisfaction of Laplace equations. And the resulting streamline shape from this equation are sketched at the right of, so you can observe it here. This is the sketch of this equation, which is equals to constant. Right? So the source is also is located at point D. So we can see point D here, somewhere here. Source is here. And the velocity field is obtained by differentiating the above equations in terms of Vr and V theta. So Vr means 1 over R d psi d theta. So our psi is here, V naught, V infinity R sine theta plus source strength over 2 pi theta. So by doing that, the theta component here is sine theta. So it is cos theta, and from here theta is disappeared. Okay, and V theta is equals to minus of d psi dr. It gives us minus V infinity sine theta. Okay, minus V infinity sine theta. So that is so equation 376 is a direct sum of the two velocity fields. As a result, that is consistent with the linear nature of Laplace equation. Stagnation point is just a point in the flow field, which is considered with zero velocity. So, which can be obtained by setting equation this the 376 and 377 equal to 0. From that, we can get a stagnation point. Okay. When we equate equation 376 equal to 0, what happens? V infinity cos theta plus the field strength z by 2 pi r is equal to 0. So just rearranging this, we can solve it for theta and r. Okay, we can solve two linear equations are there. Actually, from the second, v infinity sine theta equal to 0. So these points are points, for example, to satisfy this one, what happened? Theta must be pi at every pi, or theta must be 0 or pi. Okay, if theta is 0, this thing is 0. If theta is pi, 2 pi, 3 pi, 4 pi, this is 0. So we can put pi, n times pi here. So theta is n times pi. And we can calculate r from here. So it is just field strength divided by 2 pi v infinity. Okay, so which are the coordinates, r and the theta coordinates of the stagnation point. Okay, which is labeled as point B in the above figure. So point B is somewhere here. This line tracing is just point B. That is zero velocity point. The stagnation point is a distance, the field strength divided 2 pi infinity directly upstream of the source. For this result, the distance dv is clearly grows smaller if v is increased and larger if this is constant, is increased. Okay. So this is actually all about stagnation point. So you can read the information here. Sink and source with equal strengths. The superposition illustrating in figure 322 results in the flow over the semi-infinite body ABC. So the flow is showing A is here, B is this point, and C is here. So it gives a kind of half ellipse, okay? And this goes to infinity. A goes to infinity. That means this line extends in this way, okay? This line also in this way, so it is going infinity, okay? For only uniform flow and source flow. So if we add the sink flow, it gives another source, sink, and uniform flow. I think it is better to see that part. So when we combined source, sink, and uniform flow, superposition of uniform flow and source sink pair. Okay, this gives us an ellipse. It is called Rankine ellipse, I think. Yeah, that is called Rankine oval. Okay, it is just an oval with a shape of ellipse. And one of the focal point at the source and another focal point in the sink. So it is equation is size equals to V r sine theta plus the field strength divided 2 pi theta 1 minus theta 2. So this theta 1 and the theta 2 are the angles made for some point P from the source and from the sink. Okay. Which is located at r distance from, and the flow becomes uniform at the top and bottom here. It is kind of streamline flow. Okay? So this is source, sink, and uniform flow combination. Okay, so it is called Rankine oval. Another flow type is doublet flow. that is what we call third elementary flow type. So consider a source of strings given, source strings given, and sink of equal but opposite strings. So this is sink strings and this is source strings, which are separated by distance L. So the distance between source and the sink is separated by distance L. And the point P is somewhere there, which is drawn at θ2 angle and θ1 angle from the source. Okay, so at any point P in the flow, the stream function is defined in this way. The source string divided by 2 pi times θ1 minus θ2, which is equals to minus of source strings over 2 pi times delta theta. Delta theta indicates θ2 minus θ1. Okay. Okay, so by considering the limiting case for the doublet, what happened? When L is approaching to a small value, L approaches to 0, and L times source strings is equals to constant. We have to decompose this into what? To some theta angle. And length A is here from R, which is perpendicular here. B is from here. So this thing should be decomposed. Okay, so psi is equal to the limit of as L approaches 0 and K. K is just L times the source strings. Okay, the strings of doublet flow is denoted by K. So now for the doublet flow, we use that kappa. You can call it as kappa. Okay. Okay. So kappa is the source strings divided by times L, which is constant. So that limiting case helps us to determine the d theta. Okay. Length A is equal to L sine theta. Look here, length A is here. So this length A is equivalent with L sine theta. Theta is here. So for A, it is opposite. L sine theta is A. Then another is B. B indicates this length is actually L cos theta. So R plus L cos theta, total it is R minus L cos theta is equals to B. R minus L cos theta, correct? So d theta is equal to A over B. So just d theta A over B, L sine theta over R minus L cos theta. So finally, this helps us to give the equation psi is equal to minus of the doublet strings over 2 pi sine theta over R. Okay. And in terms of pi, in terms of velocity potential, we can define the velocity potential for doublet float is the kappa k, or the doublet field strings divided by 2 pi cos theta over R. And this is the stream function and the velocity potential for doublet flow. So there are some rearrangement to find what is there. The stream of doublet flow are obtained from the psi function, just psi is equals to constant. So from that we can obtain R. R is equals to minus of K over 2 pi C. C is constant, sine theta. And this equation gives the equation for stream in doublet flow. And recalling from analytical geometry that the following equation. Actually, in polar coordinate, r is equal to d sine theta, which is a circle with diameter d on the vertical axis, and with center located at d over 2. So this is what we call doublet flow with strength k. So the circles which we can find are k over 2 pi c. C is some constant. Okay. Okay. So here also these circles are also, and the doublet strength is pointing outward here, towards to here, because flows are from at the top it is from in the clockwise direction, and at the bottom it is in the counterclockwise direction. So the flow is like this. Okay. So this is doublet flow. The next topic is about non-lifting flow over circular cylinder. So yet we have seen how the flow over semi-infinite body can be simulated by a combination of uniform flow with source and sink. And the flow over an oval-shaped body can be constructed by superimposing uniform flow and source sink pair. So that gives us the Rankine oval shape. But in this section, we are going to demonstrate the combination of uniform flow and the doublet flow. Okay, doublet flow and uniform flow combination, which produce a flow over cylindrical circular cylinder. So circular cylinder is one of the most basic shape which we consider in our aerodynamic analysis. And the study of the flow around such cylinder is just a classic problem in aerodynamics. So this is that uniform flow, okay, which is with the stream function, which is equal to V r sine theta, and doublet flow gives psi is equal to minus of, which is with doublet strength over 2 pi sine theta over r. We sum up them. Finally, what we can get is flow over a cylinder. So this is the type of superimposition of uniform flow and doublet flow, which produce non-lifting flow over circular cylinder. So we can make some rearrangement. Let our just a mathematical arrangement. Okay. Yeah, so we'll decompose the velocity into the radial and the tangential components. So our VR is 1 minus r square over a small r square, the whole times v infinity cos theta. And the v theta is minus of 1 plus r capital R over a small r square, v infinity sine theta. So that are the velocity field, which is obtained by differentiating psi with respect to. So this is the psi equation. And differentiating VR is equal to 1 over r d psi d theta. And v theta is equal to minus of d psi dr, which is given. So based on that, what finally we get are this 393 and the 394 are the equations for radial and tangential velocity. Yeah, so these are the two velocity. And then we have to find where we can put the stagnation point. The stagnation point related with the point where velocity is 0. So the velocity which we obtain, Vr is equals to 0, V theta is equals to 0 point. When you are equating it, you can get these two equations. So these are equations for stagnation point. And simultaneously solving the two equations, we can find r and the theta. So the r, the small r and the theta are located at point capital R and 0 and R and pi. So for n pi's, okay, which are in point A and B respectively. So where are those point A and B? Point A is here, point B is here. They are stagnation points. Okay, point A, B, point A. Okay. The equation of the streamline that passes through stagnation point B is obtained by inserting the coordinates of B into equation for r is equal to r and theta is equals to pi. Okay. So finally psi is this equation. Okay, so I think we'll continue from this point for the next remaining part, and we may revise the non-lifting flow over circular cylinder in the next discussion. So this is, I think, sufficient for today. Okay, so thank you very much.